Distinguished guests, ladies and gentlemen, now let us officially commence the opening ceremony of the Korea AI Summit 2023. And welcome once again. My name is Jiyoung Jessica Park, and I've given the honor of hosting today's opening ceremony. 안녕하십니까, 여러분? First of all, I'd like to express my sincere gratitude to all of you for coming to today's event out of your busy schedules. The theme of this year's summit is AI-powered innovation, which is very timely and relevant topic to pull the collective wisdom of AI experts at home and abroad to think about AI's present, future, as well as its related challenges. And today's conference is being broadcast on our YouTube channel. Before we begin, please allow me to introduce our distinguished guests joining us here today. And please welcome each and everyone with a big round of applause. First of all, we're joined by Sungbae Chun, President of the IITP. Good afternoon and welcome. Thank you very much. And we are also joined by Mr. Junwoo Shin, Vice President of the IITP. Thank you very much. Thank you. And we are also joined by Professor Seonghwan Lee from Korea University, and he's the general co-chairs of today's event as well. And we're happy to be joined by Professor Irfan Essa from Google, and he's also the general co-chairs of today's event. And we are joined by Professor John Pons from INRIA. Yes, thank you very much. And last but not least, we're joined by Professor Klaus Robert Miller from TU Berlin. Thank you very much. Although there are more distinguished guests whom we'd love to recognize, but we kindly ask for your understanding that we cannot address all of you in consideration of the time. But once again, we really appreciate your presence. Moving forward, now we would like to take time to salute the national flag of the Republic of South Korea. I'd like to ask everyone to please stand up and look at the national flag. Salute the national flag.
나는 자랑스러운 태극기 앞에 자유롭고 정의로운 대한민국의 무궁한 영광을 위하여 충성을 다할 것을 굳게 다짐합니다.
At ease. Thank you very much. Now you may be seated. And now, I would like to invite Professor Irfan Essa, one of the general co-chairs of this event, to deliver his opening remarks. Please welcome him with a big round of applause.
Thank you. Thank you so much. First and foremost, I just wanted to say thanks to everybody for coming here, and also more importantly, thanks for inviting me to be part of this event and this organization. We are in an interesting time. AI is here. AI is actually now having an impact, and it's becoming extremely valuable on our daily lives. The most interesting thing I can say about AI right now is that it's having strong economic impact. It's changing how we think through how we do everything. And actually, to be very honest, Korea is a very interesting place to developing the next generation of AI. You folks have a lot of expertise in AI, historically coming from some of the amazing work that's been going on in your academic institutions. I was just recently also visiting with some of your corporate entities here. And even in the corporations, there is a desire not just to continue supporting, but innovating AI to the next level. And there seems to be a lot of excitement. Of course, you have a lot of corporate entities that have built some of the most advanced electronics and autonomous types of technologies here for decades, doing this kind of stuff in AI for a long time. And actually, you're well placed here because now this kind of technology is being consumed and developed worldwide. And there's a lot of opportunities here. I was just visiting, as you know, I'm also working with Google while being a faculty member at Georgia Tech. Google has a small operation here. And even Google is kind of trying to understand a company that's driven by doing AI research and development and deployment across the world, and is also wanting to engage more deeply with people in Korea because there's lots of opportunities. But at the same time, there are lots of other corporate entities. Bottom line is AI is now actually happening. I was just sitting at the front desk here with Jean and others and stuff like that, and we were basically all of a sudden noticing that while some have been working on AI for a long time, now people understand what we've been working on, and there is a lot of demand on what we're working on. I do a lot of this kind of stuff and work in AI, but one thing I'd like to always think about is you have to start thinking about AI on the long run. There is something which is referred to as the Amara's Law. The Amara's Law basically goes like this. We tend to underestimate the impact of technology on the long run. We overestimate it on the short run, which basically is what the hype cycle is about. AI is important. It's been here for a long time. And arguably, most of you used AI technology to get here. But nowadays, we're basically thinking the whole era of AI is now here changing how we do things, but at the same time, it's been doing this, that if I had a switch that turned off AI, we would all be lost. And that's the impact of AI, that as soon as it becomes valuable, we do not assume it's AI. It becomes transparent to us, it becomes part of our society, part of our activities and stuff like that. And that's the great thing about being researchers, is that we build things, and as soon as they became pervasive, we basically say, yep, let's move on to new and other forms of innovation. And that's why AI-powered innovation is an important part of what we do. Thank you all for coming here. I'm excited about all this kind of stuff, and please join me in kind of helping develop this new generation of technology. I'm glad to see all of the young students here who are going to be the ones building it all. Thank you.
Thank you very much for your valuable remarks. So he briefly mentioned the landscape and future prospects of AI and technology. Once again, thank you very much. And moving on, I would like to invite Professor Songhwan Lee, one of the general co-chairs of this event, to deliver his opening remarks. Ladies and gentlemen, please welcome him with a big hand.
Hello. We welcome you to the Korea AI Summit 2023, hosted by the Ministry of Science and ICT and co-organized by the AI Innovation Hub, the IITP, Korea University Institute for AI, and the Seoul metropolitan government. This event, AI-powered innovation as its topic, aims to bring professionals together to promote in-depth talks and discussions on the latest research trends in the field, and to discuss fostering AI experts. I express my gratitude to Josun, President of IITP, for his invaluable time spent with us today, as well as researchers and academics working on the AI Innovation Hub project this year. Professor Ivan S. of Google, who is also the event's co-organizer with me, served as the first keynote speaker. Professors Klaus Robert Müller, Jean Fongs, and Max Willing will deliver intriguing talks as keynote speakers. I hope to bring engaging discussions with other invited speakers whom I am unable to introduce individually due to time constraints. In addition, I would like to express my gratitude to Professor Shin Jin-woo, Jo Min-soo, Kim Sun-ju, Baek Eun-ok, Park Hyun-jin, and other staff who made this event abundant. It is our aim that everyone in attendance will have the opportunity to engage in meaningful conversations that will lead to future research cooperation and talent development. Thank you.
Thank you very much, Professor. As you mentioned, we look forward to sharing in-depth discussions today. Next, I would like to now invite Song-bae Chun, President of the Institute of Information Communications Technology Planning and Evaluation. He'll be delivering his congratulatory remarks. Please welcome him with a big hand.
Good afternoon, ladies and gentlemen. My name is John Song-bae, the president of IITP. I sincerely congratulate the hosting of Korea AI Summit 2023. First of all, I'd like to express my gratitude to Division Director Ri Sang-min from the Ministry of Science and ICT for attending today, but he is a little bit late. And especially I'd like to extend my thanks to Chief Professor Lee Sung-hwan, professors of the organizing committee, and all the parties concerned for the effort to host this summit. I believe that the Korea AI Summit is formally established itself as a leading international conference for sharing our country's outstanding achievements in AI technology over the world. AI is not only reshaping the competitive landscape of overall industry, but also expanding its influence beyond being a catalyst, playing a role in improving the quality of human life. Among these conforming, all countries of the world are promoting the advancement of AI technology as well as the cultivation of top-tier talent. Korea has also been proactively responding to this global trend. We have been supporting global-level AI research and talent development through AI Innovation Hub since 2019. Before we knew, the AI Innovation Hub has almost completed the first phase of research execution. In the first phase of research execution, AI Innovation Hub has created an innovative and challenging research environment in the field of AI, and also laid the foundation of the open development of human resource. I hope that Korea AI Summit 2023 will provide an opportunity to share the achievements in research and talent development. At the IITP, we will be fully committed supporting and making efforts to establishing the AI Innovation Hub as a global hub of AI research. Once again, I deeply thank you everyone for attending here today. Wish you all good health and success. Thank you. Thank you very much.
Thank you very much for your warm remarks. 네, 수고해주신 전성배 원장님께서 잠시 무대 위에 대기해 주시기 바랍니다. 잠시 후 기념사진 촬영이 진행될 예정입니다. So as we are to take a group photo with all participants, please remain on stage. And now we will have a photo opportunity on stage to capture this meaningful occasion. I'd like to invite Professor Sung-hwan Lee and Vice President Junwoo Shin onto the stage. Thank you very much. Vice President Chunu Shin. Thank you. And I also would like to invite our distinguished guests, those who are sitting at table 2. Yes, please come forward. And table 1, table 3, table 5. Please stand up and come forward. So meanwhile, I once again express our sincere gratitude to you all who are working tirelessly for the advancement of AI-related industries. So looking at the camera, I want you all to show us your big smile. So once everybody is ready, we're going to take a picture all together. 네, 다 준비가 되시면 사진 촬영 진행하도록 할 텐데요. 준비 됐을까요? 네. So it's a very meaningful occasion to capture. And now, please look at the camera. Open my count. 1, 2, 3. Please show us your big smile. 1, 2, 3. Please give us a big hand. 네, 다음으로는 저희 파이팅 포즈 하면서 한 번 더 촬영해 볼 텐데요. And why don't we pose for a photo with our fists raised to signify our determination. 제가 하나 둘 셋 하면 화이팅. 네, 화이팅 포즈 한번. 네, 화이팅 포즈 하면서 앞쪽에 카메라 바라봐 주시겠습니다. To signify our determination, open my count. Please raise your right hand in the air. 1, 2, 3. 화이팅! 화이팅! 네, 감사드립니다. Thank you very much for your cooperation. Now the photos have been taken. Please, you may return to your seats. Thank you very much once again for your cooperation, everyone. So distinguished guests, ladies and gentlemen, that brings us to the end of the opening ceremony. The second keynote speech will begin at 2:40, and I'll see you in a moment. Thank you very much for joining us. 감사합니다, 여러분. Distinguished guests, ladies and gentlemen, good afternoon and welcome back to the second session of today's event, the Korea AI Summit 2023. Saying hello to you again. My name is Jiyoung Jessica Park, and I've given the privilege to host today's conference. Korea AI Summit 2023 is being live broadcast through our YouTube channel, and I'm very pleased and happy to live stream the event as we are now reaching a wider audience online and share information and our insights. Now, I believe it is time for us to introduce our second keynote speaker. Ladies and gentlemen, please join me in welcoming Professor Klaus Robert Müller. He'll be talking about AI for getting insights from brain-computer interfacing to digital pathology. Please welcome me with a big hand.
Thank you very much. Thank you very much for having me. It's really a pleasure to be in Korea, and many of you know that I'm coming quite frequently, twice a year, and this is the third one this year. So today I will be giving a brief introduction into topics where AI helps the sciences, and because I'm very passionate about this. And also, I mean, some shameless self-advertisement. So I'm part of one of the 5 national AI centers in Berlin. I'm running the Berlin one, and there's others in Germany at different locations. And we always have welcome young and not so young scholars as visitors, and we're recruiting heavily. And probably everybody who's running an AI center these days is saying that. So I will start a bit with brain-computer interfacing, maybe a topic that I've been starting to work on with brain signals since '95, and more recently, the last 12 years in histopathology. And I will introduce a bit of explainable AI in between and conclude. So let's talk a bit about brain-computer interfacing and what it is and what the motivations are. So I had the privilege that Song-Won Lee gave a wonderful talk this morning introducing a lot of the great progress at KU on brain-computer interfaces, so I can be very short introducing this. So we mostly study non-invasive brain-computer interfacing using electroencephalography, which requires a brain and a number of electrodes, and then you have a very complex high-dimensional time series. Typically, we have measuring with 64 channels, and that becomes a very exquisite machine learning problem because we would like to decode what is happening in the brain and understand its state and understand what a subject wants. And for this, I think what I started out as a machine learning scientist, rather theoretically inclined, and I realized that this is a very challenging a topic. And it's challenging because you don't have an internet full of data. So you have little amounts of data. So the concept of learning from small data is an important thing. And it requires actually some prior knowledge, in this case, medical prior knowledge. And we could try it in a data-driven way, or we could try it together with our medical colleagues. And the latter one is much more successful. So it's one of these interdisciplinary endeavors where all disciplines need to work together very tightly. And so you can see some of the features that are well known well known from the physiological side, and they are excellent to put into classifiers, and with that we can classify a certain state. And I will give you a bit of a video that is an old one, but it's still conveying the idea very well. In this case, we have a subject that is a younger me, and the subject is wearing an EEG cap. And so I'm engaging in the game of Pong. And so what I will do in this video is I will have my EEG being measured in real time. Then there will be a decoding. And all of this happens quick enough that the feedback is given directly to the screen of my intention. So in my case, I'm actually imagining not speech, like in Song-Won Lee's talk, but left and right motor movement, but I will not be moving. So I hope that this works, yes. And so you see, I will try to hit the blue ball as often as possible. As we know from the game of Pong, this works well, and this is very reproducible. And the interesting thing is you can talk to the subject what they actually do, how to do this imagination. In my case, I'm imagining pulling a virtual string, right? And there's allegedly German professors are good at this discipline. But what can we do? with a brain-computer interface. So one thing is, of course, that we can do fundamental neuroscience. Then we can provide hope to patients for restoring communication. And there's a wide range of neurotechnology. Let me remind you, at the time when I started this, that this was a very small field with only medical groups working on it. And typically, a patient would be trained to change the brain signals so that they could be decoded with a rudimentary signal processing method. So the patient would need to spend something like 300 hours. And now with machine learning, things have changed drastically. So because you can have the subject think whatever the subject is thinking, and that the machines learn. And that reduces the training time for subjects to less than 5 minutes, or even to 0 more recently. Now, this is one of these projects that take long time and a lot of patience. I insist in this. I also would like to say that there's a lot of interesting applications, and I would just like to bring you one which seems totally obscure at the first moment. And that was about video coding. So what has brain-computer interfacing to do with video coding? So first of all, brain-computer interfacing is not only a method to communicate intentions, but it's also a method which we can understand what the thinking and behaving brain is doing in real time. So in this case, in video coding, it would be nice to know about how the brain perceives signal quality. Why? We know from MP3 that if we compress only the things that we could perceive, then we can gain a lot. And perhaps we could do the same with video coding. And I have engaged in a collaboration with Thomas Wiegand, who's one of the fathers of video coding, H.264 and H.265. He's one of the fathers of this. And I will show you a simple video getting the idea what we have been doing. So first of all, how do we measure whether the brain perceives video quality change? So the idea is to know, is a highly compressed video or a video that spends a lot of bits, can we see actually the difference? Okay, so what I'll show to you is a video that basically plays, and then at some point, there's a change in the number of bits that is in this video. And the idea here is, here you would perceive this. If you don't perceive it, then because this is an excellent projector, then you should get a new glasses. So here's a video with some scatter underwater, some checkerboard underwater. And you could see that there was a difference in the quality in between. So your brains reacted to this quality difference, something that we can measure. And this is now a small contrast. And if you know the difference, then you can see it. But if you don't know it, you can't see it. So here your brain wouldn't have reacted. So, which means that we can start quantifying effects. We can, of course, also do user studies, and these are the psychometric functions by users who judge things. But here's the basically the reaction of the brain to the change in the quality. And you can see that if the quality change is drastic, like in the first video, then we get the red curve. There's a strong reaction, and otherwise it's quite flat. And that's universal across subjects. So I'm showing you this because you can do these visual neuroscience experiments to judge whether textures, whether these checkerboard videos, all sorts of signals, whether you perceive a difference, whether they are coded with many bits or few bits. So this gives you very fundamental insights. And these fundamental insights can then be used practically, because you understand what you need to code and what not. And that can go into the next video coding standard. And that was done by the engineers that are in Fraunhofer Heinrich Hertz Institute, and they could gain something like 10% of the bits. So 10% seems little, but the amount of energy, and we've heard a wonderful talk about sustained AI this morning, the amount of energy for video coding is about, at least Thomas Wiegand says that, it's about the equivalent of 200 nuclear power plants. So saving 10 would be a good thing, right? So of course, we have to say, if we get more bits freed, then the quality of the videos will be higher, but that's a different story. So, but practically, it's a very unexpected outcome of a very basic neuroscience experiment that I showed to you. So just insisting here, we've done something which is total foundational research. Brain-computer interface is foundational neuroscience research with machine learning. And we came up with something very practical, very important for the planet. And that is unexpected, and I would call this serendipity. So serendipity happens, and we have to be open to it. So let me go to another topic, something that I have been, pursuing for about last 12 years or so. So we, my friend Frederick Clauschen, who's the last author on this paper, he's a pathologist and a physicist. And so we started engaging with machine learning to understand and classify pathological slices. And I'll show you what this is about. So here's a typical pathological slice that, okay, so pathologists are the medical people who are asked during surgery, when some tumor is cut, whether the margin is large enough. But they are also the people who diagnose, all sorts of cancerous diseases or other diseases. So they're very important, and unfortunately, there are very few of them. In Germany, there's only 12 or 1,400 board-certified pathologists, which means that, given the amount of diagnostics, it's already too few people now. And if they retire, it's a disaster, right? So because not many enough new people can be raised, so to say. And this is a disaster in all sorts of countries. Maybe the biggest disaster is in China. So we are trying to help in this context. So here we started out, because, having the pathological slice is an image that is very large. It's about 250,000 pixels by 150,000. That's the typical size. So it's much larger than your average photos. So you have to, get it into smaller parts, and then each smaller part is then classified. So which means that you classify into cancer and non-cancer. So we were quite successful doing that, and we achieved very good generalization abilities. So we were quite pleased with ourselves. But when we showed this to Frederick Clauschen, he said, well, that's interesting, but not useful. Okay, so then, well, what can we do? He said, well, just classifying is not enough. You actually need to say why the classifier comes up with something, right? And basically, this was a bit of the starting point of another endeavor, which is called explainable AI. So the abstract problem in explainable AI is, well, you know, maybe it's easier to see if you're not a pathologist and relate to. Say you have a trained model, and the trained model is getting a new image that it hasn't seen. So in this case, it would be considering this as rooster because it's been trained to roosters and dogs and buses and distinguish between all them because it's a computer vision model that is state of the art. Now, the problem in explaining why the model considers this a rooster, this particular image that it has never seen before. So what is so roosterish about it? Well, it's actually the underlying math problem is very hard because the model is a very nonlinear one. And you would have to go backwards through a very nonlinear model and then, you know, go back to the pixel space and say why this decision has been made. And, you know, it took us a while of thinking, remember our motivation, and then we could find a way to go through this nonlinearity backwards, and it was called layer-wise relevance propagation. It is a very popular algorithm these days, and it now has got many friends, and many algorithms are out there. But LRP was the first one who had a proof to it. So the interesting thing is now you can actually look at the right side of the slide, and you can see a heat map, which is green neutral, and red means that these pixels are very important for the decision making for the particular trained model. So you can see that the model considers this a rooster because of the rooster's comb, right? So this is a very difficult thing, and a fundamental math problem needed to be solved. And now we actually have some methodology with which he can inspect neural networks. We can understand why the computer vision model considers the espresso. It's because of the Kramer, as you can see. And also, we can study kernel methods, and we can know why a certain picture is considered a cat, sometimes because of the mustache, sometimes because of the fluffy bit, and, you know, maybe because it's cute. I don't know. I mean, depends on the classifier. So all of this has been becoming a big field, and you can now have graph neural networks, transformers, and even unsupervised learning methods explained. So having said this, what does explanation buy us? And this is something that I just relate to the earlier topic on cancer. So we were able to classify well, okay? So we could generalize well. Now, is the generalization error actually all that we need? We are told so in our classes, but the generalization error, just to remind you, if you have a machine learning model and data, then the machine learning model tries to be optimally parameterized to give good predictions on unseen data. That's the generalization error. Okay, so if we look at this, and we can put this into the context of computer vision, and this is like an old computer vision task from back in the days. It was called Pascal VOC. And the typical thing here is that you have two models, in this case, Fisher and DeepNet, and they classify well, both, with some differences. And sometimes, for example, in the case of the horse, the difference is not very significant. So the difference between 80 and 81% is nothing. So so if you would trust the generalization error, then in fact you would like both models and that's it. But now we have our tool, which is explainable AI. And we can now study this more carefully. So we can look at new image, and we can see both models actually say that this is a horse, because there's a horse on it, and both models have a low error, on horses. So, but we can also inspect how the models solve this by looking at the generalization error, is by looking at the heat maps. And so you see on the very right, you can see the heat map of the deep neural network that clearly identifies the object. So it's the horse's butt, the horse's nose, the rider. In the context of the middle picture, the Fisher, the strategy is quite different. So it's looking all over the place, also a bit to the horse's butt. But most importantly, it's looking at the lower left corner. Okay? And so clearly there's no horse in the lower left corner. But if we inspect this even closer, we can see that in the picture, in the ellipse, red ellipse, there's a copyright tag, which basically says Lothar Lenz, Pferdefotos.de. And so it's a copyright tag that is only in the horse class and only for 40 or 50% of the images. So what the Fisher has actually learned is to detect horses by looking at the copyright tag and not at the horse itself, at the object. So you may smile because this is a funny example, but it's actually not so funny if you have a not important question whether this is a dog or a horse. Maybe nobody dies from that, but if it's a cancer, there's a urge to get this right. So if we do cancer classification, we would rather have the right image. So because this is a very common thing among neural nets and models out there, we tried to coin some word for this. So namely, you're classifying correctly for the wrong reasons, right? And so we call this the clever Hans effect, because there's a horse, and on the left is a horse, right? Name is Hans. It's a horse from Berlin, 1900-something. And this horse was very famous because it could do math. The person shows some addition on the board, some exercise, 3 + 2, and the horse would have to give an answer to that. So the horse would use his hoof and tap on the wooden board, in this case 5 times, and the horse would always get it right. So this was very surprising to everybody on the planet, because journalists would write, horses can do math, right? Of course, at some point, somebody with more reason came and said, well, perhaps the horse is really sensitive to the human. And then they exchanged the owner with some other human, but still the horse could do the math. So they found out that the horse was really just sensitive and couldn't do any math, right? Which I think is reassuring to my point of view. But practically, the horse has always got the right decision, but for the wrong reason. And that's exactly what these models do, right? In particular, the Fisher model. It's because of the copyright tag, it's classified as horse, right? So this clever Hans effect has been going undetected in many, many applications. And maybe my guess at that time when our paper was written was that about 50% of the models out there are of this type. So we have to be very careful, in particular if we are talking about the sciences. So coming back to pathology, now we have something to make Frederick Clausen happy, which is we have a classifier, and we also have an explanation. And for this, I show you the details. So here's the heat map, but I will show you a bit more details. So you have the pathological slice, and then we classify this as cancer. And this is the heat map, and now we do an overlay. So the model has clearly understood that there are cancerous cells and is putting some, red on this, which means that it's using that aspect of the data to classify, in this case, correctly. And so this is interesting because it's not only that we are able to classify well, but also we are able to explain why. And if we think about the usage of this, then you could think that not the process of diagnosis is automatized away, but it's supported so that people don't overlook anything. So for this, we thought this is nice and good, but can we do something more? Because it's about insights. Explainable AI can provide us insights. So we can not only classify about cancer or non-cancer, but we can also classify about tumor-infiltrating lymphocytes or stroma or other aspects that are interesting for the cancer community. That's one thing. So we're using the slice, the image, and we're predicting a particular aspect. On the other side, we can use the image and predict the molecular expression. So that's interesting because if we think about it, a molecular expression is something that is measured not locally at every point in this slice, but it's just one number for one slice. So we have no idea about the resolution, why a certain molecular protein expression or somatic mutation, and whether this has anything to do with the slice. So we have about 60,000 of these numbers of protein expressions and so on. And now we can try to predict them. And most of them we cannot predict. Maybe we can predict 50 or 60, right, to a reasonable extent. And then we can look at the heat maps and we can try to get insights. And we can see whether these molecular markers have been shown to associate with the cancer in literature. And then we can put things together. We can look at, the carcinoma classification, that's the red heat map, and the green ones would be the tumor-infiltrating lymphocytes, and the blue would be some molecular property. And this allows us to quantify certain properties that we don't know before, right? So we don't know anything about the spatial distribution of these molecular markers unless we do a staining, right? So we can check this prediction and the LRP heat map by doing a new staining experiment to the tissue. And then we find actually some nice coincidence. And we're very happy about this. Okay, so now for most of you, and I think we will hear Dingang later, we hear all these stories in newspapers about AI, being, automatizing diagnosis and, being ready for clinical use. But most of this is unfortunately nonsense, and it's hype. So there are very few cases where AI is actually contributing something that is of clinical value. And I will show you one example, and Dingang will show a lot of examples, but in a different field. So here's the paper that we wrote. So remember the whole cancer project that was going on for much more than a decade, right? So this project was much quicker. And so the question was, how can we integrate histology and molecular profiling? Here's the clinical use case. So a patient comes to the hospital and has a so-called squamous cell head and neck cancer. Okay, something like in the figure in the head that you see on the left with the two blue things with the red dot. So something squamous cell head and neck cancer. So the cancer is removed, person goes home, and after 5 years or 6 years, person comes back to the hospital and has a squamous cell lung cancer. Okay, so now the question is it a primary lung cancer, or is it a metastasis of the prior squamous cell head and neck cancer? There's a fundamental difference between these two diagnoses. So if this is a primary lung cancer, then it can be removed, and the person, depending on the cancers, of course, the person can survive and become 90. But if it's a metastasis, then the typical prognosis is 3 months. So there's only palliative treatment. So if you say that this is a metastasis, but it's a primary lung cancer, which is a wrong diagnosis, and it's a bad one because you wait too long to remove the cancer and you just give palliative treatment and you wonder after 5 months why the person is not died. So under the microscope, both cancers look the same because it's squamous cell. So practically there's about a 50-50% chance just from the histopathology to decide upon this. And it's a tough case, and it always goes to the tumor board. Now, there's something that we tried. A colleague of ours, David Kappa, has established this technique in a spectacular paper in Nature in 2018. Basically looking at DNA methylation. You know, the methyl group is a CH3 group, and it's basically methylating the cytosine in the DNA. So in a way, we can think about this as our sins reflected by this methylation. So it keeps a memory of, so to say, a cell's life, say. Okay, so now machines exist where the methylation can be measured by a bit of tissue, and you get a vector of 700,000 values or 800,000. And now we can use that and build a machine learning model. So the first thing that one would, of course, try to do is use a decision tree or something very simple. You see that there's not a lot of data. So you have a primary training cohort of these squamous cell head and neck and the lung cancer and normal samples. And these are not many. And then you have a validation set. And we also have a historical set as well. So if we take a random forest at some accuracy of 99%, we have about 43% of the cases that we can predict. We have to reject many. So if we take a neural net, then at a 99% level, we can predict about 92% of the cases. So only 8 cases we need to reject. This is spectacular because it's going from a 50-50 call that you have as histopathologist to something that is, you know, at the 99% level, at least for 92% of the cases. So it's spectacular because it's of clinical value. So when my medical friends talked about this during their cafeteria, everybody was excited. And even by the time when the paper was still under review, the people came up with some cases which were of that type. And we would, of course, knowing that this is an experimental method, we would provide some way, some use of our method. And so nowadays, people like this a lot, and we are aware that we still need multi-site studies and everything. But I think this is a very valuable thing, that because it's not something rare. So this was like a data sheet that we prepared to provide as information for the tumor board that always looks at these things. So we have been, for those of you interested in our work, this is a recent review. In fact, it's already advanced online. It's in Annual Reviews of Pathology, which is the #1 journal in that field. So I will wrap up. So I think it's important to open the black box. There's a lot of different techniques for XAI available these days. Understanding the models that we're using in the sciences is of high interest, and also a good tool for gaining insights on the matter, insights that we didn't have before. One thing that I would like to remark is that this very foundational research that takes decades sometimes, it's also a very applied thing in AI. In the end, something very useful can come out of it. And this foundational research, I've seen it happening very quickly, leading to startups and new products. And just for you who are interested, we founded this company, AI Agnostics, in 2020, knowing that this was really something very useful that we did for the community. And we have now 90 people working in it 3 years after. And so I think also another lesson that I learned is we really need a good set of standards in order to achieve great results. This is great people, and this is a very scarce thing. Then we need a stable environment, stable funding, and it needs to be safe. So people should be safe engaging in long-term things. And I think most of the breakthroughs really take time, and also patience. It also takes not only patience by the researchers engaged, because people, I know Alex Binder, he started this cancer project when he was a postdoc, and now he's a full professor, right? So it takes quite a while, right? But it's worth it. And the most patients may come from funding bodies. And I think I already stressed the importance of interdisciplinary research. And we are in Berlin under the very lucky situation of permanent funding of our center. I think this contributes a lot to being able to look at really breakthrough questions with a lot of breadth, if you want. And I think with that, I would like to thank you for your patience and attention. Thank you.
Thank you very much, Professor Müller. A very interesting model of applying AI and machine learning in neuroscience and pathology. Now, we will be able to receive one question from the floor. So, ladies and gentlemen, if you have any question, please raise your hand. We will deliver the microphone. No questions? All right, it seems like there is no question because the presentation was perfect. So now we'd like to wrap up there. Thank you very much, Professor, once again. Please give him a big hand once again. All right, so that's a wrap for the second keynote speech. Starting from 3:30 p.m., cluster presentations will take place in the Royal Chamber, the private chamber on the 4th floor, and the Great Hall, where you're sitting at the moment. Each cluster will be broadcast online, and the channel information is available on our official website. Once again, thank you very much for your cooperation and your attention.
Good afternoon. My name is Taewon Kim, and I'm from UNIST. And also, I'm a session chair for this session, Cluster 3, AI for Scientific and Social Challenges. First of all, I thank you for attending this session, even with your busy schedule. Currently, Korea AI Summit 2023 is being lively broadcast online, and also you can choose whichever the cluster you prefer in official website. And this session, we have presentation with the topic of AI for scientific and social challenges. As the first presentation, Professor Jimbo Su from Molecular Mind will present his talk, and the title is Recent Progress on AI for Protein Study. Professor Jimbo Su unfortunately cannot attend, and he will present his talk through video recording.
Hello, this is Jimbo. It's my pleasure to be able to talk about my work at this conference. I really appreciate the conference organizers invited me to talk about my work here. First, I will share my slides. In this talk, I'm going to talk about the recent progress done by my group on AI for protein study. A protein consists of many amino acids. On this slide, at the left-hand side, I show you the chemical structure for one amino acid. One amino acid contains dozens of atoms. Here you can see the chemical structure for one amino acid. All the 20 amino acids in nature share the same set of backbone atoms, but they are different in the side chain, so which is represented by R on this slide. In nature, there are 20 different amino acids. Here I show you one example of a protein. So this is just an artificial protein which has 8 amino acids. So at the bottom of this slide, you can see the chemical structure of this amino acids, this protein. So you can see one protein consists of possibly thousands of atoms. All these atoms interact with each other to form a stable shape. So we can use a string to represent the amino acid sequence of one protein. For example, for this protein, we can just simply using DRVY IHPF this string to represent the amino acid sequence. In order to understand the function of a protein, it's important to know the tertiary structure of a protein, which is the atom positions, which is the position of all the atoms of this protein in the 3D space. So once we have the 3D space, once we have the 3D position of all the atoms of protein, then we can use some software to visualize the structure of a protein. So there are many different software that can do this work. So here, I show you some example of protein structures visualized by some software. So in total, you can see here there are 4 examples. So the top 2 are cartoon representation of 2 protein structures. They look very beautiful because they are cartoon representation. But in practice, a protein has a much more complicated structure. So the bottom 2 pictures show you the structure for another 2 proteins. You can see the bottom 2 structures look much more complicated than the top 2 because we use another representation of a protein structure. So there are some well-developed experimental techniques that can solve protein structures. So the first one is the X-ray, the second one is the NMR technique, and the third one is the cryo-EM. So all these techniques can solve protein structures at a very good resolution. However, these techniques, they are very expensive, and also it takes time to solve even a single protein structure using these experimental techniques. For some proteins, it's really challenging to solve their experimental structures. Like, for example, for some proteins, it may take up to 10 years to solve the structures using these experimental techniques. Since it's very challenging to solve protein structures using experimental techniques, so an alternative method is to use computers. So can we use computers to solve protein structures from given its amino acid sequence? So this problem is called protein structure prediction. The protein structure prediction problem, the definition is very simple. The input is just the amino acid sequence, and the output is the tertiary structure, which is the atom positions, which is the positions for all the atoms of this protein in the 3D space. Although the definition of this problem is very simple, but it's very challenging. So this problem is very challenging. Yeah, it has been studied for 60 years, and only until recently we come up with a solution that can predict the structure from a large percentage of proteins using AI technique. So here are 3 methods for protein structure prediction. So traditionally, protein structure prediction method is energy minimization. This is because proteins tend to fold into minimal energy state. This means that we can minimize the energy of protein to do protein structure prediction. So this method has been studied for decades, but the progress is slow and the precision is not very good. Even with supercomputers, the energy-based method couldn't predict the structure of a large protein very well. And the second strategy is using the traditional machine learning method. So this method was proposed in about early in 2000. But this method couldn't improve upon the energy minimization method. So the third strategy is to use deep learning. So deep learning was applied to protein structure prediction back to maybe 7 or 8 years ago. So deep learning can do protein structure prediction much better than the other methods. Now, by using modern deep learning techniques, we can predict the structure of a single protein chain very well. Here, I briefly list the history of deep learning for protein structure prediction. So back to 2012, deep learning outperforms all the other methods in image recognition. So back to 2012, deep brief networks have been tried on protein second structure prediction and protein contact prediction. But this DBM method failed to improve protein second structure prediction or protein contact prediction. And then in 2014 and 2015, so my group developed a deep convolutional neural network for protein section structure prediction. So we indeed, by using this method, we can improve protein section structure prediction by 3 or 4 percentage. Although this improvement is very large, but it's significant because protein section structure prediction is relatively easy. So it's very hard to improve section structure prediction. But by using deep convolutional neural network, we can indeed improve section structure prediction by a good margin. So this work indicates it's possible to improve protein structure prediction by using some deep learning methods. Then in 2016, so my group found out that by using deep convolutional residual neural network, we can significantly improve protein contact prediction and tertiary structure prediction. So this work is the first effective AI method that can significantly improve protein section structure prediction. So my paper was posted online in the fourth quarter of 2016 and officially published in PLOS Computational Biology early in 2017. So in 2018, and so we found out by applying this deep convolutional residual neural network to do the distance prediction, we can further improve protein tertiary structure prediction. And at the same time, DeepMind also developed a similar method, that is using deep residual neural network to predict the interresidual distance and then do tertiary structure prediction. So in 2018, then the community knows that by using modern AI technique, we can do protein structure prediction much better than ever before. And in 2020, so DeepMind further extended, further developed the deep learning method by using an end-to-end attention-based network. So DeepMind developed a software called AlphaFold 2. So AlphaFold 2 can do protein tertiary structure prediction much better than the method, than the system developed in 2018. So the accuracy of the AlphaFold 2 is comparable to the wet lab experimental techniques on many proteins. So this is a brief history of deep learning for protein structure prediction. And of course, there are many groups, many researchers that are using deep learning to study proteins in different aspects. So they're not only use deep learning to do protein structure prediction, but also there's deep learning to do protein prediction, to do protein design. So here, this is the first effective AI algorithm that can greatly improve structure prediction. So this paper first time show protein contact prediction can be greatly improved by deep learning, and the predict context can fold quite a few hard targets in Cameo. The Cameo is a benchmark for protein structure prediction, is an online benchmark. And we also found out, even if we don't train our deep learning method by membrane proteins, our method still works very well on membrane proteins. And we also found out, even if we train our AI method using a single protein chain, our AI model can also do very well on complex contact prediction. So this means our method has a very good generalization performance. This also means this AI method does not do prediction based on simply sequence similarity. So this paper was officially published early in 2017, and in the first half year of 2018, so this paper won the PLOS Computational Biology Research Prize in the category of breakthrough and innovation. So in 2020, DeepMind developed the second generation of AI algorithm for protein structure prediction. So in this in this algorithm, so DeepMind used an end-to-end attention-based neural network to do structure prediction. So the attention-based network is better than the convolutional neural network in that the attention-based network can capture global information better than convolutional neural network. So this is the first advantage. The second advantage is able to do end-to-end prediction. So the prediction error in the tertiary structure can be directly feedback into the input. This is the advantage of the second generation AI algorithm for protein structure prediction. So tested in CASP and in many other test proteins. So on a large percentage of proteins, so AlphaFold2 can do very good prediction. The prediction accuracy is comparable to the experimental techniques. So this slide was shown by Professor John Mote. So Professor John Mote is the founder of CASP. So this slide shows you the progress of protein structure prediction in the past 30 years. So in this picture, in this figure, the axis is the difficulty level of the test protein. So from left to right, the test proteins are from easy to the most difficult. Yeah. And the y-axis of this picture is the quality of the predicted structure. So ranges from 0 to 100. The higher, the better. You can see in this picture, there are quite a few lines. Basically, each line represents one CASP test. So all these lines, they can be grouped into, they can be divided into 3 groups. So look at the right-hand side of this picture. So you can see all these lines can be divided into 3 major groups. So the bottom group has 12 lines, represent CASP1 to CASP12. So you can see at the right-hand side, which means on the most challenging test proteins, from CASP1 to CASP12, the prediction quality is very low because all these methods, they are based on the traditional methods. Yeah, all the predictors are using traditional methods from CASP1 to CASP12. So in the middle, there are 3 lines. So these 3 lines represent the results of the first generation AI algorithm, which is a deep convolutional residual neural network method. So from here, you can see by using even only the deep convolutional network, we can do protein structure prediction much better than the traditional methods on the difficult test proteins. And at the top of this picture, so there's 1 line represents AlphaFold2. So AlphaFold2, again, can do much better than the first generation AI algorithm. So from here, you can see by using modern AI techniques, now we can do protein structure prediction much better than traditional methods on the most challenging test proteins. Yeah. So this is the progress of the protein structure prediction in the past 30 years. From here, you can also see for a very long time, by using traditional methods, no matter how we try to improve it, the prediction accuracy couldn't improve a lot. So this indicates the importance of AI for protein study. So now we know AI has revolutionized protein study. Here, on this slide, I briefly show you the history of protein research and AI study. So back to 1960s, protein study and AI study, they are 2 independent topics, independent of each other. Only until about 10 years ago, AI is gradually applied to protein study. So the breakthrough point is in 2016 when I developed the first deep convolutional neural network method for protein structure prediction. Yeah, so in 2016, yeah, we know AI can do very well on protein structure prediction. And then in 2018 and 2020, so DeepMind developed a better AI system that can do protein structure prediction much more accurately, further improve protein structure prediction by using modern AI techniques. Since 2020, many researchers are now using AI to do protein design. So in the past 1 or 2 years, so AI is transforming protein design. Now by using AI, we can design proteins much better than before. So in this slide, I summarize what can be done by AlphaFold and what couldn't be done by AlphaFold. First, AlphaFold can do very well on the structure prediction of a single protein chain, and AlphaFold can also assign very accurate confidence score on the predicted structure. However, AlphaFold is not very good at protein complex structure prediction, and it couldn't predict very well the antigen-antibody binding pose. And also, AlphaFold depends on the evolutionary information encoded in the multiple sequence alignment. So when a protein understudy does not have any sequence homologs, then AlphaFold couldn't do very well. This means AlphaFold couldn't do structure prediction very well on orphan proteins. And further, there are also quite a few problems that cannot be solved by AlphaFold. For example, AlphaFold couldn't be used to couldn't directly predict the effect of a single mutation or multiple mutations. And AlphaFold couldn't do antibody design, couldn't do directly do protein design. And AlphaFold couldn't predict very well the interaction between proteins and other molecules, like proteins and ligands, and proteins and RNA DNAs. And AlphaFold 2 couldn't directly do protein optimization. So this is why we needed to develop other AI methods to solve all these problems. So here, I summarize the AI algorithm developed by my team in the past 1 or 2 years. So on this table, I divide the algorithms into several categories. Like, so for example, some algorithms have already been applied to industry, and some algorithms are under wet lab validation, and some algorithms are only benchmarked using some public data sets. Like say, for example, for protein optimization and some vaccine optimization and enzyme optimization. So these algorithms have already to industry for antibody structure prediction and for antibody humanization and for protein de novo design. And so these algorithms are under wet lab validation. So due to time limit, I'm not going to details for all these algorithms. So in this talk, I will just show you, just present some of our algorithms. So first one is for the antibody structure prediction, because antibody is a very important drug. So here I show you the prediction accuracy of our method on antibody structures compared to other methods. As shown in this table, so the bottom row is our results. So we measure the prediction error by RMSD on different regions of the antibody. Like for example, we measure the prediction error on framework, on CDR1, CDR2, or CDR3. And then we also compare our methods with a few other methods like AlphaFold 2 and Hitchfold single and other methods. So in this table, you can see, so our method has a minimal prediction error among all these methods compared. And we also test our method on another antibody dataset. Again, we see similar results. So our method has a minimal prediction error among all these methods we studied. Here is the results on nanobody. Again, on nanobody, our methods has a minimal prediction error. So in addition to do protein structure prediction, we also developed quite a few methods for protein design. So here I briefly explain what's protein design. So protein design means we want to create proteins that do not exist in nature, which means we would like to find one amino acid sequence adopting a user-defined structure and performing desired function. Protein design is a very challenging problem. This is because, first, sequence space is huge. For example, suppose we want to design a protein with 100 amino acids. Because in nature, there are 20 different amino acids. So in total, there are 20 power to 100 possibilities. Among all these possibilities, there's a very small fraction of proteins that can be folded into a stable structural formation and also can perform desired function. So in order to do protein design very well, we needed to be able to predict the function of a desired protein very well. So this is the basis for protein design with a specific function. So protein design, protein design is slightly different from protein structure prediction. For protein structure prediction, the input is only the amino acid sequence and the output is the structure. But for protein design, depends on the application scenario, there may be different input. For example, sometimes we need to design the protein backbone and then corresponding sequence. And in other cases, we may just want to design protein sequence for a given backbone, or we may just want to design the function site. So it depends on the application scenario, we may have to develop different methods for protein design. So here, I'm going to show you one protein sequence design method. Yeah, we just developed this method that can simultaneously do protein side chain packing and protein sequence design. Protein sequence design is also called inverse folding. So already quite a few programs that can do protein sequence design, like protein MPNM. So our method is different in that while we design protein sequence, we also make use of side chain information. So here, I list the advantage of our method for protein sequence design and side chain packing. So this is the first, this is the end-to-end AI algorithm that can directly predict the 3D coordinates of side chain atoms, and also runs much faster than the traditional side chain prediction methods. And this method can design protein sequence while considering side chain conformation, and no other AI method can do so. And there's no AI algorithm that can simultaneously predict side chain atom coordinates and design protein sequences. So here I show you the difference between protein structure prediction and protein sequence design. So for protein structure prediction, the input is the amino acid sequence, and the output is the 3D coordinates for all the atoms. And for protein sequence design, usually the input is the protein bond and the output is the amino acid sequence. So this way, protein sequence design is also called inverse folding. So we developed a method called attention packer. So here we use attention-based network to do protein side chain packing and also protein sequence design. So on this slide, the left picture shows you the network architecture we are using for sequence design and side chain packing. So input is protein backbone. So here we use a graph to model a protein backbone, which means each residue is modeled as a graph vertex. And when two residues they are close to each other in the 3D space, then we add one edge in the graph to connecting these two residues. Side chains, atom coordinates, and also optionally design the protein sequence. And we don't have to design the whole protein sequence. So here we can use the mask to design only partial residues in this protein. So there are different masking schemes. So we tried the linear mask, which means we just design the amino acid for a segment of protein. And we also tried random masking and also structure-based masking. We found out the best strategy is to mix all these masking schemes and to train our AI method. Then our method can do the sequence design better than any single masking scheme. So here I show you some results. So this table shows you the sidechain packing results on the CUSP14 test proteins. So we measure the sidechain packing quality using the prediction error like RMSD. We also measure the prediction error of the chi angles, and also measure the prediction accuracy of the chi angles. And also we measure the steric clashes among the predicted positions. So this table shows you, so no matter which metrics are used, so our method outperform the other methods like the very popular school and also the recent deep learning method, DL Packer. Then for protein sequence design, we also measure the native sequence recovery rate. So as shown in this table, so our method has the best native sequence recovery rate. Then we also calculate the energy of our desired proteins and then compare the energy to the energy of the native proteins and to the proteins desired by Rosetta design. So as shown in this picture, the yellow point represents the proteins designed by Rosetta, and the green point represents the proteins designed by our method. So from this picture, you can see our desired proteins have lower energy than those designed by Rosetta, and also have the lower energy than the native proteins, which means our method can design energy more favorable proteins, which is usually more stable than the proteins designed by the other methods. So in addition to protein sequence design and protein sidechain packing, and we are also developing a method for protein docking and also antibody design. So using another AI method. So here is the definition of a protein docking. So input are several unbound proteins, like say 2 or 3 unbound proteins. Then the output is the binding poles of the input proteins. So this is the definition of a protein docking. And so this method, this algorithm, not only can do protein docking, but can also design one protein or a partial protein for another protein that can bind to another protein. So here are the input feature used by in our AI algorithm. So we consider 2 types of features. One is features associated with a single residue. The other features are associated with a pair of residues. So here we use distance matrix to represent one protein structure. We also use a metric, an orientation matrix to represent a protein structure. So we stack all these matrices together. We stack the matrix with individual proteins together to form a large matrix. So we input this large matrix and also the single residue features into our network. So here, I briefly, I just simply show you the our AI algorithm, the network architecture of our AI algorithm. So please look at this slide from right-hand side to left-hand side. So our AI method consists of one encoder and one decoder. Encoder is used to capture information in individual proteins, and decoder is used to generate the theoretical list for the complex. It's used to generate the complex structure. So due to time limit, I'm not going into details. So here, we use several data sets to train our AI method. So first we use single protein chains, and then we also use protein complexes to train our AI algorithm. In order to do antibody antigen binding plots prediction, and in order to do antibody design, we also train our AI algorithm, our method using 3,000 antibody antigen complexes. So our loss function includes pairwise distance and per residual LDDT and the violation loss for physically realistic conformations. And also our loss function include the frame and line point error, which is used in AlphaFold 2. So yeah, we train our AI method in 3 stages. In the first stage, we train our method using both complexes and single protein chains. And in the second stage, we train our method only use the complexes. And for antibody antigen prediction, then we fine-tune our method using the antibody antigen data sets. So here I show you some results. So on this slide, the table here show you the docking results on one antibody benchmark dataset. Please note here, our input are unbound structures. Yeah, here is where we must be very careful to not use the bound structure as input. So we measure the quality of our prediction using several metrics, like say we use the DOG-Q success rate. We also use the interface RMSD and the ligand RMSD. So our method can also generate top 5 solutions. So we look at the quality of the first prediction as well as the quality of the best of top 5 predictions. So in terms of the DOG-Q, so our method is the best among all the methods that we compare. Like say, our method is better than AlphaFold 2 multimode, and also better than traditional docking method like ZDoc, and also better than the recent deep learning-based docking method, EquiDoc. So yeah, no matter we look at the top 1 solution or the best of top 5 solution, our method performs the best. So in addition to do well on protein docking, our method can also be used to do antibody design. Like say, we can redesign the CDR region of the antibody. So yeah, so one company test our method on one target HER2. Yeah, to design some antibodies for this target and did some wet lab experiments. And they found out, so among 100 designed antibodies, 41 had very good affinity to the HER2 protein. And also, the designed antibodies is more like natural antibodies and also has very good specificity. Okay, finally, I'm going to show you some real-world applications of our AI algorithms. So here are some projects we are working on. So first one is we have applied our AI algorithm to develop cytokine drugs. So we found out, so by using our AI algorithm, so we can develop very good cytokine molecules. So on this slide, the right-hand side, so are 2 pictures, 2 figures in the bottom. So this is the test results on mice. So these 2 pictures shows So our desired molecule has a very good activity, can suppress tumor very well, and also does not have a very serious side effect. And we also applied our AI algorithm to design protein vaccine. Yeah, we combine language model, evolution model, and structure model, energy model to design vaccines. And we also did wet lab experiments. So among only a dozen of variants designed by our AI method, so 2 exceeded the publicly reported or patented molecules. And the binding affinity of our molecule, so we have improved the binding affinity. So our molecule has much better binding affinity. So it's fourfold better than the best molecules patented by big pharmas. And we also applied our algorithm to do enzyme optimization and de novo design, so we can improve the thermal stability of enzyme as well as the activity of enzyme. And we also can do de novo design of enzymes. So all our algorithms are now integrated into one platform called Molecule OS. So Molecule OS is a cloud-based AI platform for protein modeling and design. So this platform consists of 4 layers. The bottom layers are our large protein foundation model. And then the second layer is our capability layers. This capability layer contains quite a few function modules, like, for example, for protein structure prediction and protein induction prediction, protein function prediction, and the prediction of a single protein mutation or multiple mutations, and the protein optimization and the de novo design. Then we combine some function modules to and apply and then apply them to a specific protein modalities like enzymes or antibodies. Finally, then for specific products, then we can have some solutions like, say, for enzymes, now we have solution for enzyme optimization and de novo design. So yeah, we are training our large protein foundation model for protein generation, for protein de novo design, and many downstream tasks. Yeah, so we train our model using several types of protein data. In addition to protein sequence database, we also use protein structure database and a protein function database and protein body interactions. Finally, I summarize my talk here. So this is the take-home message. So AI has revolutionized the protein structure prediction and now is transforming protein design. So there are various applications for protein design. Protein design can be applied to drug discovery, to synthetic biology, and to agriculture and environmental improvement. Thank you so much.
Thank you, Professor Chimbosu, for inspiring talk. Unfortunately, we cannot take any question, but again, I thank Professor Chimbosu for your presentation. Then next we move to next presentation. We have next speaker, Professor Eun-ok Baek from Hanyang University. And her presentation title is Default AI for Protein Structure Prediction. Please welcome Professor Baek.
Thank you. So this is it? Okay. All right. I'll be talking about another AI model for protein structure prediction called DeepFold, developed our research group. Well, Professor Jinbo Xu has already given a nice introduction to structure prediction, so I'll be very brief on that. And then I'll present our work on DeepFold and our results
from last year's CASP competition. And then I'll describe the work in progress and how we prepare for the next year's competition. Well, as been already said, protein's function is defined by its structure, and its structure is determined by its sequences. And proteins are key molecules of life. It digests the food you ate during this lunch, and it carries oxygens in your bloodstream, and it allows your immune system to recognize foreign antigens like spike proteins of coronaviruses. Okay? And AlphaFold came up in year 2018 and gave us a start of a solution to this 50-year-old grand challenge in science. As you can see here, is it? No. As you can see, AlphaFold performance is almost the same as what's been experimentally validated. But however, still, various attempts are being made all over the world. Actually, there are these big tech companies like Meta and Baidu. They are also developing AI models to predict protein structures. Although AlphaFold predicted over 200 million protein structures and published it last year, there are still a lot more to be done. On your right, you can see these bar charts where the blue means the known protein structures and those that can be derived from those experimentally determined structures. And the red and orange represents what AlphaFold has added. Okay. If you look at the human proteins, you can see that AlphaFold has almost double the number of structures we can use, but it still covers only about 60% of the entire human protein. So there are a lot more to be done. And the deepfold actually is a modification to AlphaFold 2, which is more or less the same for every other efforts currently ongoing. And we made 3 major changes to the AlphaFold 2. One is we came up with a different method to generate one of the inputs to the AlphaFold 2. And then we also modified certain functions and losses in the structure module of AlphaFold 2. And then also we optimized energy functions. We redefined the energy functions used in structure reoptimization model. Okay, here, the input feature generation. AlphaFold, other than the query protein sequences, AlphaFold takes 2 more inputs. One is MSA and the other is template. MSAs are just a collection of protein sequences from a variety of organisms, which are similar to the query protein in their sequences. And if all these protein sequences from a variety of living organisms are aligned in a certain way, you can recognize which part of those sequences are conserved. And that gives very important information for AlphaFold to use to predict the protein structure. So for MSAs, we haven't done actually all that much. We simply used multiple search tools to collect more sequences to be used as an input as an MSA. For templates, we used a different alignment that's been developed our team that's based on conditional random field. And when the overall structure is compared with AlphaFold 2, you can see on this, sorry, on this left chart, you can see that there is not so much of a difference, although default showed a little better performance than AlphaFold 2, but they're more or less the same. But when you compare their alignment quality, you can see that there's some prominent differences between the two. So we did the experiment of using AlphaFold 2 as is, and then using AlphaFold 2 with our novel template generation method. And when that's compared, we can see that there are a lot more target proteins whose score is better than AlphaFold 2. If you take one of those target protein, T1064, its MSA is pretty low quality. So when MSA isn't giving enough information, template can be very helpful, we believe. So this is the end result of this target, and that's the native structure, and this is what default has predicted, and that's the AlphaFold 2 prediction. And you can see that there is a huge difference between the accuracy of structure between these two predictions. Whereas the initial input of template wasn't all that much different. It was 0.3 versus 0.4 between the two, but the end result was significantly different. We believe that this is because MSA isn't helping at all, whereas template is doing a lot of work, and that can lead to good results. And another modification we did was adding certain functions and changing loss functions in the structure modules. And there are a lot of efforts, but I'm going to mention just one of those, sequential condition torsion angle loss. Amino acid side chains are consisting of atoms in sequence, and their torsion angles must be predicted. If the first torsion angle is wrong, then correctly predicting the second torsion angle is sort of meaningless, because it's going to be wrong anyways in the end results. So we thought that we have to modify the loss function so that the torsion angle loss should be conditioned on the previous atom's torsion angle. So that's what we did. And it's really important to have a side chain structure accuracy high, because whenever this protein is interacting with some other molecule, like Professor Xu has just shown, it is important to have a very accurate side chain structure. So that's what we did. And if you compare the side chain accuracy between default and AlphaFold 2, there's not much of a difference, but in many cases, default gave better side chain accuracies. Okay, last year there was this CASP competition, and there are two target categories in CASP competition. One is TBM, template-based modeling, and the other one is free modeling. And template-based modeling targets are those for which we have known structures from which we can compare with the query protein, whereas FM targets have no such known structures. So those are difficult ones. And this was the first time we entered the CASP competition, and we ranked 4th, which is not bad. And when we focus on TBM targets only, we ranked 1st. And you might think that, oh, TBM targets are easy, and being 1st in the easy targets doesn't really mean anything. But the TBM targets means that there is a lot of information about MSA and templates. So all the other tools had more or less the same input, and the difference mainly comes from the AI model, we believe. And as you can see here, the differences in the scores are not that big. They're all pretty much the same. That's because all these contestants use the same AI model based on the same AI model, which is AlphaFold 2. So that's what we understand as our results. And here are some interesting examples where we failed pretty bad. And one target here is consisting of 5 free domain, 5 FM domains, and 1 TBM domain. And this gray line here is the top ranked prediction. And ours is this cyan line, which is pretty bad. And similarly here again. And we believe it's because we haven't put much effort on MSA input. So next thing we will do is we'll put a lot of effort into coming up with a better MSA input for the prediction. Okay, so currently we are working on getting more and better data for training. So we collected a bigger database and filter them and cleanse them and do a lot of data engineering to be prepared for the next year's competition. And as I said, we didn't do much with the MSA part during the last competition, so there's a lot of room for improvement in MSA. So we can adopt more advanced search techniques, and we are working on coming up with better embeddings using maybe language models or some generative models. And in the case when MSA or template are not available, then we might want to resort to a single sequence model like ESM-fold or Helix-fold. Okay. And we are also interested in updating this template feature again. In this case, we want to come up with an end-to-end learning model that can be done with the differentiable Smith-Waterman algorithm for the alignment. And we are interested in coming up with a better embedding for sequence and structures. So there might be some improvements over there as well. To make our computational resources more efficiently used, we are trying to parallelize both model and the data at the same time. And yeah, it's an ongoing work. Finally, we are working on this mixture of experts architecture where each expert learner is focusing on different parts of the input protein sequence. And this gating network here sort of soft switches between different experts. I haven't got into the details, but we noticed that AlphaFold 2 and thus default as well is not good at predicting structures for proteins with a lot of helix structures. So maybe we are thinking we can come up with an expert on helix protein structure prediction so that that part can be better equipped to give the overall result better than before. Okay, so we have been working on default and entered this competition for the first time, and we hope to get a better result next year. The thing is, AlphaFold DeepMind had updated their progress the day before yesterday on the last day of October, that they have come up with the newer version of AlphaFold called AlphaFold Latest. Their version is not a number yet, but it's called AlphaFold Latest. And there they can not only predict a single monomer protein, but they can predict structures for protein complexes, proteins interacting with ligands, or proteins interacting with RNA or DNA, and proteins interacting with another proteins. So yeah, DeepMind is making a big step, and we will be pretty busy for the next coming months to catch up on that. Okay, that's it. Thank you.
Thank you, Professor Beck, for inspiring talk. Do you have any questions? Please raise your hand, and mic will be given. Any questions? In the meantime, I have a question for Professor Beck. So I saw that there are several proposed components compared to AlphaFold, and which component do you think most important for performance gain compared to AlphaFold?
It's hard to say, but I think the template alignment part was helping a lot for certain cases, and the metrics that are used to evaluate the results are there are a variety of different scores that's used to evaluate the prediction results, and it depends on where you focus on. And we were focusing mostly on sidechain accuracy. So I think in that respect, we obtained the goal that we have been working on. But next time it may be different. Okay.
Thank you. Any questions? If there is no other question, then we conclude the presentation. Thank you, Professor Beck. Next speaker is Professor Jinsul Kim from Gangnam National University. And this is the last presentation of this session. And the title is AI and Energy, Solutions for Sustainable Energy. Professor Jinsul Kim, please.
Thank you. All right. Good afternoon. I'm Professor Jinsul Kim in Gangnam National University. Yeah, I'm very delighted to share the insight today in my presentation. Our title is Bridging AI and Energy Solution for the Sustainable Tomorrow. Actually, our project, our research is conducted as part of a 12 project within AI Innovation Hub, this government project. We focus on meta-energy intelligent. Yeah, so we dedicated address the various challenging in the energy industry and daily life, and through our research efforts and collaborating with the 16 professor and then a lot of researcher in this research. As you look at this, it's Gangnam National University, and then GIST, and Jeonbuk National University, and Caltech, and Seoul National University. So we work together. And we aim to pave the way of the sustainable future. Okay, how can control? Oh, yeah. Here is the agenda. First of all, I briefly explain of our research significance. And next, we discuss about our research there are three domain issues. First is cross-domain energy management, and second, I explained understanding energy phenomena, and then last is the high-dimensional energy transformation, and then okay. I think everybody knows this Ali bag, actually, Ali 100. Yeah, we Korean, we always say it's Ali bag. Yeah, Ali 100, you know. So, yeah, you know already is how much Ali 100 important issue in the world, you know. So, energy actually play a various role in our, you know, life, and then powering technology and the industry. So utilizing the AI in the energy sector poses the unique challenge, such as handling sensitive data and then addressing data and reliability issue. So our research aim to overcome those challenges and focus on the task like energy demand forecasting and efficient building management and energy-centric natural language processing and proactive issue and predict and then resolve. So our goal is to improve the energy industry efficient and sustainably, and then decision making. So we term these technologies meta energy intelligent. So as you look at the this this PowerPoint, and the deep learning can really uncover and analyze the pattern within the power data, and then the power actually the image data and openly inceptuable to the naked eye can be inspected efficiently. Especially in the best area like the solar site, and using drone, you know, using drone, and then something vision data we can use. On the bottom, on the left, the time series data can reveal the hidden characteristic specific to different time zone, including time 1, 2, 3, and then we divide that and analyzing to improve the energy efficiency. In the bottom of the you know, it's some Korean words is explore the deep learning technology to provide the depending outcome for critical managing decision. So, okay, as you look at this, you know, recently AI advancement helped lead to a surge in the data center usage. That's data center. Oops. Yeah. Yeah. Maybe in your institution and then any other, you know, company has a lot of like that data center. So which come with high cooling energy consumption we need. Let's look at that video clip. Okay. Yeah, great.
This is a box full of computers, and the computers are immersed in an inert oil. So an oil that doesn't harm the computers, quite the opposite, it actually helps the computers. There are no fans, so it actually protects them. And what happens is the oil, the computers in the oil, the computers heat the oil up. The oil then flows through that pipe over to the other side of the plant room. It flows into a heat exchanger, and in that heat exchanger, the hot oil meets the cold water from the pool. So the hot oil is flowing through those pipes, down here, and into the heat exchanger. Yeah, indeed. It's
Yep. So, yeah, to solve a lot of problems, we use the AI, but using AI, that means we consume, consume a lot of energy. So it's kind of nonsense, we have to use AI and using a lot of big data, right? But we need we always problem with the energy consumption. So like that short video clip, there are various methods for the solution, including submerging data center under water to repurpose the excess heating. So similarly, more effect is required to harness AI to enhance the power efficiency and minimize the carbon emissions through the improved energy efficiency. Okay, here is our object of our research. The object of our research, let's explain this shortly. There are three main domain, and then portable. We research about the cross-domain energy management research. It is investigating energy management technique across the different domain. Second one is high-dimensional energy data transformation. It is exploring the multidimensional, high-dimensional transformation and reliability in energy time series data and the image. So in the figures, energy data from the various industry will be utilized for the data extraction and supplementation and reliability enhancement, and to apply diverse learning method. So the deep learning model will be investigated to address the complex industrial challenging using multidimensional time series and then image data. Yeah. Next, we research technology for the understanding energy phenomena, which is the vital for the fact-based decision in the energy sector. Actually, we're using some natural language technology. In the natural language processing, there are a lot of applied to energy tech, AI technology. So we address the challenging like hallucination and some intending misinterpretation, and aim to assist the human decision making in the energy field by complex pattern in the energy data. So the figure, we aim to help human decision making through energy knowledge graph or the multimodal meta learning that can be extracting from energy text and time series data and the multimodal heterogeneous data. The human level energy technology. It is we try to developing energy technology with human level understanding, and then capability to achieve human level performance and promote collaboration with the real world application. So it is our main figures. So we own the extract energy knowledge from diverse industry data to aid decision making and then developing human level energy path prediction and then managing technology using deep learning, derived data, meta dimensional and the configuration explanation data. Yeah, so those technology hold the great promise, can contribute to various benefits and include energy efficiency improvement and energy supply and energy demand prediction. Energy grid management also include, and cost reduction, and then environment prediction, and ultimate promotion sustainable energy production and the UGA. So through those efforts, we aim to impact the diverse industry and sector for pursuing the green plant. So yeah, let's explain more detailedly in our research part. So first, I explained the cross-domain energy management research part. It is there is some delay net. We made that delay net. That means this one is about efficient temporal, dynamic, and future mapping for energy platform. We call the delay net. So this delay net is optimized the energy domain prediction by enhancing temporal future extraction using delayed convolution. It means the TCN localization feature while efficient handling long sequence. So the figure, delay net utilized the pattern specific feature in the power data, then ensuring the right weight design with preserved performance. So in the graph, there each part has they are very sensitive in the energy data. So we analyze and control, try to control that. Next, it is research about the electronic vehicle charging scheduling algorithm based on the energy consumption pattern. This research, the EV charging scheduling algorithm, is based on energy consumption pattern considering potential power demand. So for cost-effective industry application in the limited power situation. So actually, the electronic vehicle has a lot of some limitation environment, and then also the battery also has like that situation. So any other limitation environment, we try to get some efficient energy, efficient. So we focus, this study focus on the enhancing power efficiency through the DDPG and then HER algorithm, considering TOU-based consumption and the EV charging demand on the shown on the right. This is also another research. Is it on the graph? So you can look at the edge node and each point. So this study is based on the edge node in the power system to respond the constraint in the power energy. So we create an economic dispatch simulation in the edge node power system and train the AI model using defined dependent variable as shown on the graph or diagram. And also this one, also energy, we considering some set of Lagrangian for economic power supply, and then develop the algorithm for simulation on optimize it. Yeah. So this one is we use some solar energy, like Ali 100 something like, renewable energy using this research is to optimize the microgrid integration, and then apply the electronic vehicle. So on the right side diagram illustrate it the simulation for the optimal control algorithm, and allow the real-time adjusting based on the energy demand and the supply. This one also research about something, electronic vehicle, to develop and create algorithm to minimize electronic vehicle charging cost and factoring the grid constraint, charging the traffic simulation. Yeah, this one I can skip. And then this research actually communication may be restricted in the distribution system. So we try to enhance the closed loop distributed system production by replace the traditional algorithm with some deep learning model using LSTM. And so we improved the limited need for the communication, reduce installation and operating cost for communication equipment. So in the figure on the right, illustrate the closed loop distributed system with limited communication, where our deep learning model alternative 96% protected system accuracy, and then 93% detecting classification accuracy. You get that? Yeah, this one we research on the insulating voltage using machine learning, introduced the novel streamer propagation feature, and proposed a method to remove electronic field gradient. So next. Yeah, this one we using solar energy. Apply the solar energy play substantively role in the domestic energy production. In our technology, we utilize the solar data from the institution, and then we using some digital knowledge Austria Solar Center to get it from that center, that data, and then we compare, and then we get some strong solution. We constructed a robust model that considers the data pattern and ensuring accurate prediction, and factoring the various such as the climate and the solar module type. So yeah, the figure we are conducting research on the improve the solar energy prediction using data from our institution and then GST and CNU, Gangnam National University, and then international source from DKASC in Austria. Okay. Okay, this one is I want to more explain. In this part, the second part is to understanding energy phenomena. So I introduced two projects. One of that is we researching how to understanding energy related text data and expressing of intent by addressing hallucination issue in language model. So our approach involved decomposing input data into the individual factor and using large language model for query generation and document retrieval and verification and text correction to mitigate the hallucination problem. So in the figure in the bottom of left is a present diffusion model that output more fact-based than conventional model by reoccurring the level of the output. The figure on the right is represented the language model, including decomposition algorithm unit that can alternate with the Hell equation. Okay, this one actually we're using the applied some knowledge we in research in AI. So how to understanding and then design to enhancing problem related to information through search within the knowledge base on to improve decision making, to combine reinforcement information with the large language model, internal knowledge. So these projects allow us to improve the energy related decision making of ability to language model. So in the bottom figures is the technology to improve responsible accurate by using two-step search processor to select the related document and check the internal knowledge when a user query. Yeah, actually we have time limit, so I choose a couple of projects to explain. Yeah, this one actually, yeah. From now is high dimensional energy from transformation research part. We're gonna explain. I gonna choose two of them. You know, so next. Okay, this one actually we researched the morphological attention loss function for detecting specific morphological characteristic of energy equipment detection. By combining prediction from the multiple model and using ensemble technology, we improve the accuracy. So as you look at the figure in the left at the bottom, you know, we're detecting some morphological characteristic in the energy equipment and improve the prediction accuracy in the best any weather situation using ensemble the technology. So next, another one. Okay, I'm gonna explain this part. You know, this research is we apply the self-supervised temporal corresponding learning algorithm with cycle constant achieve state-of-the-art performance. So particularly in the video analysis task, so this has the practical application, including challenging in respect of power facility using drone. As you look at in the beginning of the presentation, you know, a lot of energy facility using drone instead of human. You know, so that means we can use any vision technology and then video analysis technology also. So as shown in the right, you know, figure, the study was conducted to enhancing the utilization of energy postulate image by utilizing self-supervised space-time response learning technique. All right. Yeah, time is already gone. Okay, this one, last one. Okay, so this study actually tackles the lack of energy image data using some zero-shot referring image segmentation technique. So as you know that, you know, we need a lot of data to get the accurate result. But these days we research a lot of part, you know, even if the data is like that zero-shot image processing technique. So it leverages pre-training claim model for zero-shot transfer, introducing global local contexting feature for the constant text image applicant. So the figure, we introduced a zero-shot referring the image segmentation method that align local and then global feature of both image and the text and achieve superior the performance compared to the existing weekly supervisor approach. Yeah, actually we have a more issue for high dimensional energy transformation, but the time's gone. As you have, do you have any question? Maybe, yeah, I'm gonna explain the next time, right? Yeah. Yeah.
Thank you for inspiring talk, Professor Jin-Sung Kim. Since we are over time, we don't take any question right now. And again, thank you, Professor Jin-Sung Kim, for presentation. Thank you.
Thank you.
So this concludes this session for Cluster 3, AI for Scientific and Social Challenges. Again, thank you all for the great talk for speakers and also all attendees, and also all attendees online as well. So we have break time until 5:10, and from 5:10 p.m., Sparrow session will start. And Sparrow session will also be in this same place, the Great Hall. Thank you.
Time period, there will be no time for Q&A, but these are all posters outside, so people can ask questions outside at the poster sessions. Thank you very much for your understanding. All right, with that, I will go to the first presentation, and this will be given by Jae-Young Kim from KAIST on the topic of prefer to classify, improving text classifiers via auxiliary preference learning.
Thank you for kind introduction me. And hi everyone, my name is Jae-Young Kim and I'm from KAIST and I'm supervised by Jinwoo Shin. So in this talk, I will present my recent work that titled Prefer to Classify, which is accepted in the recent ICML. So in addition to the development algorithm and the hardware, the construction of the large human annotated benchmark like Squad Glue or the recent Big Bench is also plays a key role in the success of NLP system as a compass to guide the researcher in the right direction to develop the method. So usually these benchmarks are constructed by following steps. So first, collecting some relevant input text, and for the these input text, labeling them by the human annotators. But arguably, collecting the relevant input is more costly and cumbersome because if there is some distribution shift or the sparse patterns, then these things can make the model suffer being generalized. So much higher cost is often paid to the collection process in input text to keep the quality. So it could be more preferred to pay additional human cost to the auxiliary annotation instead of the collecting more input text to improve the label quality with the more annotators or obtaining the final task information with a new label space. So in this work, we propose a new alternative way to better exploit the existing benchmarks via auxiliary annotation called preference. So our idea is using the task-specific preference between the input text as an auxiliary annotation. Here, the preference can be understood like this. So there are two tags, and we can ask that which text is more positive or not. So if it is considered the more positive, we can call it as a more preferred, as a positive sentence. So our idea is using this kind of task-specific preference to improve the text classification system upon the existing task annotation like the sentiment. So by relatively ordering some pair of tags and better calibrating them with respect to the tags through this kind of the pairwise comparison, we believe that auxiliary preference learning could provide additional informative training signal to the model that cannot be captured by the instance-wise task annotation in the original label. So specifically, we propose 3 different types of the preference label in the practical scenario. And also we propose a novel multitask learning framework that can train our model with the task and preference labels called the prepare to classify. So our first idea is utilizing the recent large language model like the GPT-3 to generate the preference labels, and we call it as a generative preference. And in experiment, we actually utilize this kind of the prompt. And also another idea is utilizing the existing data annotation record. And our intuition is that if the one sample is voted with the more annotators as a positive sample, then we can consider it as a more preferred sentence as a positive sentence. And lastly, we also collect the real preference labels directly asking the humans utilizing the some system like the AMT. And actually, these 3 different preference labels has a distinct characteristics. So, for example, extractive preference can be obtained from the free. So, if there is a data set annotation record in the data set. So, but in contrast, subjective preference can be more expensive, but it can be expected to be more accurate. So with these gathered preference labels, we propose a method to train our classifier with both task labels and preference labels. So first, we introduced the diverse multi-preference head. So we first add some preference predictor beside our classifier head. And instead of the single preference head, we introduced multiple preference head and also impose some diversity regularization to maximize the information can be gathered from our preference labels. Moreover, we also introduced called the constancy regularization to explicitly impose the intuition that preferred instances should has a higher confidence. And also, we proposed a sampling method based on the disargument and the inconstance. During the experiment, we first verified our method improvement with the generative preference. Here, we observed that our method constantly effective in improving the performance in both accuracy and calibration. And also, more interestingly, our method outperforms the GPT-3 baseline with 0 shot to the 20 shot. It indicates that our method does not just distilling the just instance-wise the information, but successfully gather new information from the pairwise comparison with the preference label. Also, we verified the improvement with the extractive preference, and actually compared to the other baseline that utilizing the dataset annotation record, our method outperforms these baselines with and most 4% of the relative test error reduction. And lastly, we compare our method, compare the performance of improvement with the different preference labels. And here we observe that the subjective preference are the most effective for improving the accuracy and the calibration. So this is the end of my presentation, and please ask me or visiting the poster if there is a question. Yeah, thank you.
Thank you very much for the presentation. Thank you. Just next on, we will have a presentation by Jong-in Park, also from Yonsei University, on the topic of dual path adaptation from image to video transformers.
Hello, everyone. I'm Jong-in Park from Yonsei University. Today, I'm going to talk about dual path adaptation from image to video transformers, which is published at CBPR 23. We started this work with two main questions. The first one is, how can we leverage well pre-trained foundation models? Since fine-tuning the model from scratch is getting more costly and expensive, there have been some works to efficiently transfer the pre-trained models to downstream tasks. The second question is, can we leverage pre-trained image models for video understanding, such as video action recognition? Interestingly, the pre-trained clip can capture semantically or visually related regions in a stacked image, as shown in this figure, and this inspires the architecture of our work. In this work, we aim to transfer parameters of the pre-trained image foundation models to video domain and attain comparable performance to video models with small number of learnable parameters. To this end, we employ a dual path design of the conventional 3D CNN models. Specifically, our method consists of the temporal and spatial path. We perform temporal and spatial modeling in each adaptation path using adapters while freezing the pre-trained image model. In the spatial path, we transfer the powerful spatial context modeling capacity of image models to video data by learning parallel adapters that can keep the original features as the following equation. The red and blue boxes represent the trainable and frozen layers, respectively. In this path, each frame sampled from a video is fed into the model, as in the original image models. The output from the last transformer block for each frame are averaged to obtain the global spatial representation. In the temporal path, we should learn relationships between frames for temporal modeling. To this end, we transform multiple frames into a single grid-like frame set so that the model can see multiple frames in a single image. To enable the model to have temporal modeling capacity, we use serial adapters, largely transforming the output of the transformer blocks. The global temporal representation can be obtained as the same as the spatial path, and the global spatial and temporal representations are concatenated, and we perform action recognition with the classifier. We evaluate the action recognition performance with various backbones. With dual path, we can achieve high memory and computational efficiencies and obtain comparable performance on the Kinetics 400 and SSV2 datasets. We can see that the model captures the spatial and temporal contexts to recognize actions in the videos, as shown in these examples. Please refer to the paper for more details and results. If you have any questions, please feel free to contact me. Thank you for listening.
Thank you for this presentation. Thank you. The next presentation is, I'm sorry for slaughtering that name, Kwang Hee Vo from Kyunghee University on the topic of compress and accelerate binary neural networks with computation rearrangement.
Okay, so good evening, everyone, and welcome to my presentations. Today, I'm going to present the topic compressing and accelerating the binary neural network with the computation rearrangements. And my name is Theo, and I'm from Kyunghee University. Okay, and I will follow this outline. So as we know that recently the deep learning have been widely applied in many applications for the practical applications. But now because of the higher requirements, so that means the DNN model now is more complicated with more hardware, more resources and computational cost. So there are many existing working on compressing the model, for example, the pruning, quantization, or efficient architectures. But binary neural network is the special case of the quantization with just only one bit for the representation on the activation and also the parameters. So by using the BNN, we can simplify the computation for the multiplication, for the adder tree, and also for the max pooling, and also the batch norm with just some of the simple operations. So in this presentation, based on an observation that we can calculate the one output channel by using another output channel in the convolution with the binary parameter. So that means we can reduce the computational cost by review again the one output for another output calculations. So that means now there's the requirement that we need to have a tree that can cover all the output channels, and also the tree should be the shortest and with the shortest depth to reduce the latency. So on the screen, this is the step-by-step how we can reorder. That means rearrange the computation in the one convolution. Based on the weight filter, we can have the adjacent matrix, and then we can construct the fully connected graph, and then we can explore the minimum spanning trees based on the fully connected graph. And finally, we can rearrange the computation on the convolution layer by using the MST that have the shortest depth. So on the screen is the relation between two output channels in the convolution, and also we can apply it for fully connected as well. And this is the proof of the relation between two output convolution and also the fully connected graph. So, and you can see that by using these rearrangements computation on the convolution and also the fully connected graph, a fully connected layer, so we can have the compression ratio on the screens. And also to further compress the model at the training phase, we also add another new loss in the original loss, and then we can both optimize on the original loss for classification, and also we can reduce the size of the minimum spanning trees during the training phase, and then we can apply it for the inference task. And to support for the training algorithm, we try to create the one streaming accelerator on the periods to support for that kind of models. And on the screen, and this is the in the figure 6, this is the high speed hardware accelerator for the BNN. And these the application studies related to the training process and also the comparison on state-of-the-art with the hardware implementations. So you can see that at the first time of the training, we can reduce a lot the number of parameters and also the bit of optimizations, and also accuracy just reduce a little bit for the fine tuning. And we also do the comparisons with the state-of-the-art method on the ciphertext and also the ImageNet. And by just apply only the minimal spanning tree rearrangements on the pre-trained models, so we can reduce more than 50% of the bit operations on the BNN. If we try to apply the learning optimization, we can reduce maybe from the 50 to 75% for the bit operation and also the parameters. So in conclusion, in this presentation, this is the first time the binary and also the convolution characteristic are combined to utilize to reduce the bit op with the minimum spanning trees, and with the learning optimization and reordering calculation with the minimum spanning trees, we can reduce a lot of the bit operations for the hardware architectures. So thank you so much. These are all my presentations.
Thank you very much. Thank you. Thank you for this presentation. The next presentation we'll have by Tongyeon Park from Postec. And the topic is stable and consistent prediction of 3D characteristic orientation via invariant residual learning.
Hi, my name is Chonghyun Park, and I am PhD student at Postec, and will present our paper Stable and Consistent Prediction of 3D Characteristic Orientation via Invariant Residual Learning. This is a joint work with Seung Kim, Yoon Jung, Jae-sik Park, and Min-Soo Cho. So let's assume a canonicalized curve. Then we can define the characteristic orientation as the deviation from the canonical orientation. There is two properties that the canonical orientation should satisfy. One is the stability. Stability means that a single point cloud should always recover the same canonical orientation. The other one, the consistency, indicates that different point clouds from the same category should have the similar canonical orientation. Previous approaches, including canonical capsules, Condor, VNSPD, all have several limitations. First, they usually rely on point cloud reconstruction for canonicalization, which limits their approaches to per-class training. And they usually focus on stability, not the consistency. So we present our method Choir, characteristic orientation predictor with invariant residual learning. Choir can train with multi-class training and without point cloud reconstruction. And we also introduce invariant residual learning for both stable and consistent prediction. Here's an overview of the Choir. And Choir consists of two main modules. First, SO3 equivalent orientation hypothesizer and SO3 invariant residual predictor. Let me explain step by step. First, given a randomly rotated point cloud, we predict SO3 equivalent orientation hypothesis and by using vector neurons. Then we canonicalized both the input point cloud and the SO3 equivalent features into SO3 invariant quantities. Note that these quantities are SO3 invariant. Finally, we predict SO3 invariant residual using a powerful point cloud network, a point transformer. Then we finally predict characteristic orientation by multiplying the initial orientation hypothesis with the invariant residual. In this way, we maintain SO3 equivariance. And the powerful point cloud network enables both stable and consistent characteristic orientation. Here is the quantitative results, and our method achieves better stability and consistency benchmark results. And as shown in the figure, our method can canonicalize differently rotated point clouds within the same categories. Since we can canonicalize different point clouds, we can use it to pre-canonicalization for 3D perception, for example, part segmentation. Canonicalization with our method, Choir, helps non-equivalent neural network to predict rotation-robust 3D perception. So here is the qualitative results, and you may find out our method can canonicalize rotated point clouds into the canonicalized orientation. So in summary, we present Choir for multi-class characteristic orientation estimation without point cloud reconstruction. And chemicalization with Quire enables rotation robot 3D perception. Thank you.
Thank you very much. Thank you for this presentation. The next short presentation will be given by Jonghyun Kim from SNU, Seoul National University, on the topic of GVCCI, lifelong learning of visual grounding for language-guided robotic manipulation.
Thank you. Okay. It's kind of different what I expected, but can you see everybody very well? Okay, that's good. Hello, everyone. I'm Jonghyun Kim from Seoul National University, and today I will talk about our work titled GUTSI, not GVCCI. Yeah, a lifelong learning framework of visual grounding for language-guided robotic manipulation. So, the goal of language-guided robotic manipulation, LGRM, is to correctly locate and manipulate objects based on natural language instructions. So for an example, if I say, pick the bottle in front, the robot has to know which object I'm talking about and manipulate accordingly. Current works in LGRM typically follow this framework. It first infers the location of the queried object with the visual grounding model and manipulates the objects based on the inferred location. Here, we focus on visual grounding part in LGRM. Most of the previous works have trained the visual grounding model with public datasets and used the frozen model to infer in real-world scenarios, assuming that the public datasets are a good proxy for the real world. But as you can see, most of the public datasets are quite different from the environment where the robot operates. We tackled this domain gap between the public datasets and the data observed in the robotic environment, which could severely limit the manipulation ability. Thus, our framework GUTSI, which stands for Grounding Vision to Ceaselessly Created Instructions, takes raw images from the manipulation domain to adapt the visual grounding model by automatically generating instructions. Since our framework enables robots to adapt to specific manipulation environments only with raw images, it can be easily utilized in any domain where the robot operates. So this is the overall framework of GUTSI. GUTSI consists of a lifelong learning phase where the robot continuously learns visual grounding without human supervision, and the inference phase where the robot conducts LGRM. In the lifelong learning phase, it first extracts the objects and their corresponding visual features from the raw image. Then pseudo-instruction is generated through the predefined templates using the extracted object features. Now, what we have is a self-generated triplet consisting of a given image, the target object's coordinates, and the pseudo-instructions, which are stored in the buffer that stochastically forgets the earlier collected data. Finally, GUTSI updates the visual grounding model using the stored data. And the inference phase starts when a user instructs the robot to manipulate objects. The robot predicts locations of the target object and the target position by leveraging the visual grounding models from the lifelong learning phase. In the experiment, we compared our framework with two baselines. The zero-shot baseline is the one that trains the model with public datasets, as explained earlier, and pseudo-Q baseline leverages raw images from the manipulation domain, but uses the instruction generation method proposed by pseudo-Q. We have confirmed that the zero-shot method, which solely relies on public dataset, struggles to locate objects when it comes to the real-world environment. On the other hand, our framework consistently improves visual grounding as the number of observed images in the manipulation domain increase. Lastly, we have also conducted an online experiment with the physical robot performing pick-and-place tasks. Through the experiment, we have demonstrated that our method significantly improves the robot's manipulation ability. Although our work does not claim to capture all possible human instructions, we believe it represents a valuable steps towards making intelligent robots capable of understanding natural language instructions. Thank you for listening.
Thank you very much. Thank you for this presentation. The next presentation will be given by Soyeon Lee from Korea University, and she will talk about brain-to-speech, neural speech synthesis based on deep generative networks.
Hello everyone. I'm Soyeon Lee from Korea University. I'll present our study, Brain to Speech, which is a neural speech synthesis technology based on deep neural networks. Brain-computer interface, which is BCI, is a technology of interpreting and converting a user's intention to the external world without really saying or moving, but just using brain signals. And NeuroTalk is our proposed framework, which converts brain signals such as EEG during imagined speech into a real speech of the user's own voice. So if you imagine water silently or internally, then our system converts the brain signals into real speech and outputs the speech audio. Brain-to-speech technology, we call this BTS, is a novel research stream integrating BCI, deep learning, and speech synthesis technology. This aims to directly convert brain signals into audible speech. Spoken speech, mime speech, and imagined speech are the three main speech-related paradigms that are used in BTS studies. And I'll introduce our overall frameworks. First of all, imagined EEG is given as an input to the model, and the final output is the reconstructed voice. The imagined EEG and spoken EEG is converted into a feature embedding and given as an input to the generator. And the generator generates a MEL spectrogram from the feature embedding, and the reconstruction loss is calculated between the differences between the ground truth MEL spectrogram and the generated MEL spectrogram. And the discriminator classifies the validity of the reconstructed MEL spectrogram and calculates the adversarial loss. And we use the pre-trained vocoder to convert the reconstructed MEL spectrogram into a voice, and then apply the pre-trained ASR model to convert the reconstructed voice into a text. And then we applied a domain transfer learning method for transferring the overt speech-based technology into imagined speech. And this is the detail of generator and discriminator. We use pre- and post-convolutional layers, and bidirectional gated recurrent unit, GRU, was applied. And also, multi-receptive field fusion modules were applied. And for the vocoder, we used pre-trained Hi-Fi GAN, and for the ASR model, we used pre-trained Hubert. And the training losses were as follows. For the result, we have voice reconstructed from EEG, and the reconstructed cases successfully displayed similar patterns to the original voice of MEL spectrogram. And even for silent and unseen cases, the system have shown potential in generating reasonable outputs. We used RMSC, CER, and MOS for the evaluation matrices, and we performed quantitative and qualitative evaluation of spoken and imagined speech cases. This is a demo audio of reconstructed voice from EEG, while this is the original voice. We reconstructed voice from spoken EEG like this. It's quite well reconstructed. And we also reconstructed from imagined EEG, which is like this. It's quite well reconstructed. And this work was presented this year in AAAI. and we're
Thank
now
you.
working on advancing this to the sentence level. Thank you for listening, and if you have any questions, please feel free to ask.
All right. Thank you very much for this presentation. All right. And the next and final presentation for this session will be given by Seung-min Oh from Gangnam National University on meta energy intelligence.
Hello, I'm the Seung-min Oh, a PhD student at Gangnam National University. Today, I'm going to introduce some of the representation study on the meta energy intelligence. This is the agenda of the presentation. I will outline the research objective, emphasize its importance, and introduce the three main research domains. The objective of our research are the cross-domain energy management research, the investigating energy management technique across the different domain, and high-dimensional energy data transformation, exploring the multidimensional high-dimensional transformation and the reliability in energy time series data and images. Thus, we conduct the research that enable the understanding of phenomena in the energy data that are difficult for human to understand. And finally, we aim for the human level performance of energy artificial intelligence, the technology. We collect the energy data in the industry. We transformation it into the high dimensional data or the understandable information and use it to research the prediction and management. So it is the research domain. The first research is a delay net. Delay net is the efficient temporary dynamic and picture mapping for energy platform. The delay net is inspired by the TCM model. And delay net use the delay dilate convolution network to maintain the localized picture while handling the long-term dependence efficiently with the pure parameters. And second research is the solar power prediction. We utilize the Digital Technology Australia Solar Centre Alice Spring dataset and incorporate data from the PV panel dataset and solar dataset at GIST. Then considering the various external factors like the acquisition, the frequency, or the climate or PV panel type to enhance the prediction accuracy. Second part is the addressing the hallucination of problem in the NLP. Our research involved the department of the diffusion model for faithful text generation. This model verified the element of the response with the user intent, ensuring greater reliability in the answer provided. And furthermore, we are completed the technique, the decomposing atomic unit into the input data, enabling the parallel approach that help elevate the hallucination more effectively. And this third topic, the enhancing point detection in energy flexibility, we are develop an attention network that focus on specific morphological feature to improve the point detect on the performance. So addressing issue caused by the crack or the dent due to the external environment factor that may compromise data stability or the reliability. The last one is our research, the efficiently tackle the problem of limited image data. So we're using the two modules. The one is the presenter point selection and inference. This approach utilizes the pre-trained semi-supervised model to identify the object location by extending the high and low activation map within the image. Thank you for listening.
Thank you very much for the presentation. And thank you everybody here as well. This concludes the presentations for the Spotlight session today. Thank you again to all the presenters and to all the attendees here in the room and online. And the second day of the AI Summit will start tomorrow from 10 a.m. onwards, and I hope to see you all then as well. Thank you very much.